Welcome to Sigmoid's Tech Talk. My name is Shyam Choudhary, and in this session, we are going to talk about recommendation system. So let's first look at what a recommendation system. So recommendation system is a tool or framework which is used by business to provide users with tailored suggestions or advice. And this tailored system is based on users' preferences, behavior, and historical data. Now let's look at what different business use cases are available for recommendation system. So recommendation systems are used in various industry domains like e-commerce, media and entertainment, social platform, etc. Amazon and Flipkart uses recommendations to provide item recommendation to the site users. Right, and now let's understand why do we need a recommendation system. So recommendation system provides personalized user experience and content curation, which helps in improving user engagement and leads to better conversion and sales, and finally helps in improving customer satisfaction and loyalty. Now let's look at a high-level architecture of a top-end recommendation system. So this system begins by taking into account user interest and then generate candidate keys based on a data set of similar items. For example, user interest here can be headphones, and then the system will generate different candidate keys based on a similar item data set, which can be a data set of different headphones. Then this candidate key list will be ranked. This can be based on the price of the headphones, colors, manufacturer, etc. And then they will be filtered. So let's say the user has shown interest in Sony headphones, so this filtering will be done based on the manufacturer, and this can be Sony. And finally the list of product will be given as recommendation to the user. To build effective recommendations, we have certain data input requirements. First, we have user and item data, so which includes user details like the likes and dislikes of the user, their personal information. Item data, it can be anything from categories, subcategories, price, colors, manufacturer, etc. Then we have contextual data. It includes relevant information from current situation or environment, for example, seasonality, locality, etc. Next, we have social data. So social data includes details on friends, follower of the user. And finally, we have interaction data. So interaction data is a mix of user item interaction. So for example, in case of movies, it can be the rating provided by the user to the movie, the likes, dislikes, etc. Right? Now let's look into what are the different types of recommendation system. So first, we have content-based filtering system. So this type of recommendation systems are based on the similarity of item characteristics or content. So for example, if a user has shown preference for an action genre movie, then the system can recommend another action genre movie to the user. But they have some limitations like inability to recommend items outside of the user's known preferences. Right. Next, we have collaborative filtering. So this type of recommendation systems are based on the preferences and behavior of similar user. For example, if two users have shown interest in a movie, same movie of action genre, then another movie of same genre can be recommended to the user. We have a limitation here also, for example, cold start problem, where we have limited or no data for a new user or new items, which leads to difficulty in providing recommendations since we lack data for that particular user or item. The third type we have is hybrid solution. So this kind of recommendation systems are a combination of two other different recommendation system. For example, content-based recommendation system and collaborative recommendation system both can be combined to provide a hybrid solution. They have their advantages, like it helps in enhancing recommendation quality. It will address the problem of cold start as well as the data sparsity problem, and it will provide more diverse set of recommendation system. Again, Netflix movie recommendation system is a good example of hybrid solution, but since hybrid solution is a combination of different recommendation system, they have increased complexity and computational overhead. Now, once we have built our recommendation system, we need evaluation metrics to check how good our system is. So we have some tech related metrics like mean absolute error, RMSE, MAP, etc., which will tell us how technically accurate our model is. And then we have some business related metrics like diversity, coverage, which will let us know how diverse and how good of a coverage our recommendation system has. Thank you. That's it from this session. See you in the next one. And in this session, we are going to talk about the singular value decomposition algorithm. So let's start with the introduction. First, what is SVD? So SVD is a matrix factorization technique which is used as a dimensionality reduction method. And what it does, it transforms a data set from its original n-dimensional space to a lower k-dimensional space, right? And it does that by capturing the most important patterns present in our data. So how does it work? In the context of recommendation system, SVD helps us in identifying the latent factors or features present in the data, and we use those latent patterns, latent factors and features to provide recommendation to the user based on the user item interaction that we have available. Right now, why should we use SVD for recommendation? So we have three simple steps for it. First, we are decomposing the user item interaction matrix, and then we represent it into a lower dimensional space, and from that lower dimensional space we are able to identify the patterns and data patterns and latent factors present in the data to provide the recommendation. Right, now let's go step by step through the SVD algorithm. So first we have data preparation. On the left side you can see three different users and the ratings those users have provided to different items. So in this case there are 5 different movies of different genres available and the ratings provided by those 3 users. So our first step will be to convert this tabular data into a user item interaction matrix. And here we can also see that user 2 has not provided any rating for A2, so we have NA here, and similarly user 3 has not provided any rating for A1, so we have NA here. Our next step will be to replace these null values with either 0, or you can replace them with average value for that particular user. Once we have replaced them, this is how our user item interaction matrix will look like. The next step will be to decompose this user item interaction matrix into 3 different matrices called as U, sigma, and V to the power t. Our first matrix called as U is an orthogonal matrix with left singular vectors. So each column in this matrix captures pattern among the rows of the original matrix, right? So each column here will represent patterns in the rows of this matrix. So basically patterns of the users. Next is a singular matrix called sigma. So it has diagonal values, singular diagonal values, and this singular value represent the importance of or magnitude of each latent factor. So the higher the value, the better, the more the importance of that latent factor. And finally we have V to the power t matrix. It's an orthogonal matrix with right singular vectors, and each row capture the patterns among the items of the original matrix, right? So first matrix will capture patterns among the users, and the last matrix will capture pattern among the items. Once we are done with the decomposition of the original matrix, our next step is to reduce the dimensionality by selecting a subset of the most important latent factors, and we do that by selecting a value called as k, and this k can be determined by scree plot, evaluation matrix, or cumulative explained variance. In this case, if we take k equal to 2, then we will take the top 2 or the 2 most important latent factor out of the 3 present with us, and we drop the last one. Since we are taking only these 2 latent factors, we will keep 2 columns from the U matrix and keep the top 2 rows from the V to the power t matrix. Right, so here we have selected the most important latent factor from user interaction, and here we have selected the most important latent factors from the item interactions. And once we are done with this, we will combine these 3 matrices by taking the dot product to create the final matrix after applying SVD and reduction, right? And then we can use this matrix to provide prediction. So for user 1, this 5 ratings are available to us. For user 2, this 5 matrix, 5 ratings, etc. And our final step here is recommendation. So if we want to provide top n recommendation, in this case, we can provide top n items with the highest predicted rating for each user. So for user U1, we can have A1 and A2 as the highest recommended movie. For user 2, we can have R1 and R2. For user 3 also, we can have an R1 and R2 as the top 2 most recommended rating. Right. Similarly, we can provide item-based collaborative filtering recommendations. So items similar to those the user has already interacted with or rated highly can be given from this table. So since user 1 has already seen action 1 movie, we can also recommend action 2 movie to this particular user, and then user can provide rating to it. Right? So this is how recommendation can be provided with the help of SVD by applying the SVD algorithm, then doing the dimensionality reduction, finding the patterns, and providing recommendation to the user. So that's it from this session. Thank you. In this session, we are going to talk about neural collaborative filtering and its architecture. Okay. So let's start with the introduction. In the last session, we discussed about matrix factorization and how it is used in recommendation system. So what we do in matrix factorization is basically we decompose the user item matrix into lower dimension, and the goal for doing that is trying to find out the latent factors or the hidden patterns present between the user and item interaction. But there are some limitation there. The one of the basic limitation is that it cannot capture, integrate, or complex dependencies that are present between user and item. It's good for finding linear relationship that are present, but non-linear dependencies are difficult to find using matrix factorization method. That's where neural collaborative filtering comes into picture. So what is neural collaborative filtering? So it's a advanced approach in recommendation system, and it leverages deep neural network, and we can call it as an advanced version of matrix factorization, and it will help us in capturing not only linear relationship but also non-linear relationships. There are two basic components in neural collaborative filtering. First is called as generalized matrix factorization component, and another is multi-layer perceptron. We'll talk about these two models in next slides. Next, before moving on to the architecture of NCF, let's discuss about the type of feedback that we receive from users. We have explicit feedback and implicit feedback. So what is explicit feedback? Explicit feedback include direct interaction of users with item, and these are easy to capture. The example of explicit feedback include likes or dislikes, ratings, reviews, etc. On the other side, implicit feedback include indirect interaction of users with item, and user satisfaction is not that easy to track here. And the example include clicks, watching videos, the amount of time that you have watched a video, the wish list you have, wish list, etc. Right? And NCF focuses on implicit feedback. Let's look at the high level architecture of NCF. First, we have input layer and the embedding layer. So in input layer, we have the user item matrix, you can say. Next, we convert them into one hot encoded sparse user and item vector. Next layer will include the embedding layer, where we embed, we provide a dense layer to embed the user item latent vector. The goal here is to create vectors from the user item data that we have available, so that this can be fed into the next neural CF layer. So neural CF layer include two components, as we discussed, GMF and the MLP layer. And the reason for converting it into embedding layer is so that it can be fed into the neural network layer. And finally, we have the output layer, where we are trying to predict the score YUI, where it will have label as 1 and 0. 1 means the item U is relevant to the item I is relevant to the user U. Now let's look at this GMF layer. So GMF layer basically follows the traditional matrix factorization. The goal here is simply to find the linear dependencies that are present between the user and item interaction, right? So we take the user item sparse metric, convert it into the user item sparse latent vector, then finally create an embedding layer and take the dot product of both user and item latent vector to create the final embedding output of the GMF layer, right? And then it will go into the neural MF layer and finally the output. Next, we have the MLP layer. So in the MLP layer, again, we take the user item input, convert it into the embeddings, and then we pass those embedding into the different neural network layers, right? So this is where neural network comes into picture. We can have as many layers as we want based on our analysis of the data. The use for having MLP layer is to try and find the non-linear dependencies or the complex patterns that are present in our data. So this is where it becomes an advanced version of matrix factorization. This follows the traditional neural network approach, and we are trying to find the non-linear dependencies that are present in our data. Again, this goes into the final UMF layer. So this is how our final architecture will look like. So what we are doing here is basically we are ensembling two models, GMF and MLP. We will fed separate embedding layers into the GMF module and the MLP module, and finally we will have their embeddings out, and we will concatenate them to get the final neural MF layer, and finally use that to predict the score YUI, and which will have label 1 and 0. 1 which basically means the item I is relevant to user U. Yeah. So this is how the neural CF layer architecture look like, and that's it for this session. Thank you for